Hello everyone. In today's lecture, we will be starting with example how we can test the continuity of the system before we proceed to the control design part. Then we'll start the most important part in this course, how we can design controller for the system. If the system has noise or process noise, measurement noise, then how we can design a suitable controller so that the system noise can be mitigated. At the same time, also we can track the desired value of the states. So let's start the lecture. Lecture number 8. So in today's lecture, we'll be discussing test of controllability of the system. So this is very important part before you proceed to the control design, whether all the states are affected by control input or not. And second is controller design. So we'll start with the state feedback control concept. So these are the topics we'll cover in the lecture. Let's start with the example. Let's assume we have a system x1 dot equal to minus 2x1 plus x2 and x2 dot equal to, and also we are having u here. Control input is acting only in the x1 dynamics, and x2 dot equal to minus x1 minus 3x2. So this is the example test controllability of the system. If you notice in this equation, u is acting in the x1 dynamics. So if you using u, if you can control x1, also this x1 also you can control. Using this x1, you can control also x2, because anyways, here this is a negative part. This is already in control state. So now let's start the solution. So as you have done in the previous lecture, the controllability test matrix, as you know, P equal to, we can, since this is the second order system, okay, one thing I have to write here. So the state space formulation of the system, we can write x1 dot, x2 dot. This is already in the OD form, first order OD. So we can write the coefficient minus 2, 1, minus 1, minus 3. And this is state vector x1, x2. And we have the control matrix here, 1, 0, and u. So basically we are getting the state space formulation of this system. So here, this is our A matrix, this is B matrix, right? So using A and B, we can test the continuity. So we can find the P matrix B and this AB. This is second order system. The dimension of the matrix 2 cross 2. So we can go till AB. And the value we are getting 1, minus 2, 0, and minus 1. So if we find the determinant of Q, it is all not equal to 0. So if this is going to satisfy, you can say system is controllable. And another, if you want to use the MATLAB, in MATLAB code, we can write, we can put A matrix as minus 2, 1, minus 1, minus 3. And B matrix 1, 0, transpose. And so P, we can write CTRB. Continuity, we can write CTRB. Simply, we can write A comma B. And after having P matrix, we can use R for rank. So we can rank of P. So if you enter this command, we'll get R equal to 2. So since the system has dimension 2 cross 2, so we're supposed to get the rank of the matrix 2. So it is, you can say, it is basically full rank, hence system is controllable. Okay. So this is how we can test the contributor of the system. If you have the bigger matrix, you can also test. So we have taken the simple example. So now we'll start the controller design process. This is a very important part in this course. So we'll be using pole placement design concept. So here the topic is pole placement. Design using full state feedback. From this title, it is very clear that we are going to place the desired, we are going to place, suppose the system is some poles, for example, here or here or here. So this is, let's assume these are the poles we are getting from the original system. For example, this is unstable anyways. Now we are going to choose some desired pole. How desired poles may be in the left-hand side maybe here, here, or here. So how we can place these poles in such a way that these poles will follow the dynamics of these poles. So using these poles, we'll have some characteristic equation, and the result of the response of this actual characteristic equation should follow the result of these pole locations. So this is, we are going to shift this pole this side, so that overall system's response, control system response will follow the desired characteristic equation. So as we proceed, you will come to know, you will understand step by step this part. So let's assume we have a system or plant is described by x dot equal to, we are taking the most critical case, taking everything into the system so that it will not be difficult for you. If you even later, if you want to ignore some kind of function in the system, you can. So we are taking the most critical case. AXT plus BUT plus FXN of T. And the Y system, the output equation, CXT plus DUT plus EXN T. So this is the plant. So here, X is the state vector, X desired, we are choosing X desired, for example, X desired to be tracked, desired state vector that needs to be tracked so that the system will be controlled. And our XN here, noise state vector, and So these are the and A and B are the system matrices, A, B, C, and D. But here the important stuff we have introduced here, F and E. So F, here F and E are the coefficient matrices of noise in the system. So this is the plant we are going to control. So now the next question is how we can design controller so that the system will be controlled. So if you notice here, we have desired state to be tracked, and also we have noise in the system, right? So we have to define a control algorithm in such a way that the noise term will tackle, and also the system overall response will track to the desired value. So we are defining the control algorithm. The control algorithm, we are choosing U of t equal to k x desired of t minus xt minus kd x desired of t and minus kn xn of t. So here, if your desired dynamics, or if we assume desired state vector, it's non-zero, while designing control algorithm, we have to take some function in the control input like this. And this is the noise part. Also, you are introducing in the control. So Kn should be twinned in such a way that Xn can be mitigated in the closed loop system. This is the most critical example where we are taking all the consideration in the system. But as we proceed, we'll come up with this complex problem. For the time being, we are assuming X desired to be some zero value. So we want to design a regulator where the desired value of the state to be zero. So some assumption, but as we proceed further, later stage, later we'll be taking very complex case. For the time being, for making our problem simple and understandable, we are assuming the desired state to be zero. Okay. So assumption X desired of t, we are assuming zero, and also we are assuming the noise of the system to be zero for the time being, but in the next lecture, maybe we will not consider these values to be zero. Okay. So in this case, our U of t will be k x desired t minus x of t. Okay. And no, it will be simply, this is zero actually. So it will be minus kx. Now, if you come up the closed loop diagram of the system, this is our closed loop control block diagram. It will be very helpful for you how to understand this problem. So this is our controller. This is the controller. In the controller, we'll be designing A. And this controller output goes to the plant. Okay. This is the plant. The plant is nothing but our x dot equal to ax plus bu plus f x and t. This is our plant. And also, so you can assume some process noise coming into picture, process noise. And this is the output from the plant. And we are having the feedback here. So we are not, also we can take sensor noise, maybe sensor noise is there. Instead of these, we can change the background a little bit. So here we are having the sensor. This is basically sensor particle. So in sensor also you are having some measurement noise. So this is the, and also you're having the desired state xt. So in this case, xt is 0. So our the state vector y equal to cx should track the desired value. Instead of this, I can write simply x. So our main aim is as time tends to infinity, x should track x desired. Okay. So now if you notice here, so this is the error from the system, this is negative, this is positive, right? So here, if we assume, since we have assumed there is no noise, so XL we are assuming to be 0, right? So what you are doing, whatever output available here, let's assume the same output also available here to get the error. So from this we can write error equal to x desired minus x. But if for this problem, we are assuming this to be 0, right? So we can write equal to minus x. And so we are multiplying this minus x with this k vector here. So our overall control output, which is going to the plant, is u. So I can write u equal to minus x. So whatever things we have done here, it is validated also with this equation, right? So I hope it is clear. So now, based on this assumption, our system dynamics get reduced to system dynamics get reduced to x dot equal to x plus bu and y equal to cx plus du, right? This is a system dynamics. But if you follow some standard book, most of the books they are using this structure. Most of the book they are not considering the noise, but we are trying to see how the controller can be designed for if there is noise in the system. Okay. Now, since we are working on control part, so we'll substitute. So our control is equal to, this is our controller. This is the control equation. So we'll substitute this controller. Yeah. Okay. So in this case, our if you substitute u equal to minus case, then we can write x dot equal to ax minus b kx. We can write, from this we can write a minus bk into x. So this is, if you notice carefully, this system become some very nice form, right? So now, if you can find the eigenvalues, you can easily find the eigenvalues of this, and these eigenvalues will be function of k here, because a and b are known for the particular system, right? So we are defining this as equal to, we can define a CL x. CL for closed loop. Why closed loop? Because we have closed the system. Initially it was open loop. We have introduced some control here, which makes the system closed loop. So that's why ACL nothing but the system matrix of the closed loop system. This is sometimes also we call augmented matrix. Okay, augmented system. So now I'll write a note here, very important here. So the closed loop, we know that closed loop poles are eigenvalues of ACL, that is obvious. So if you would like to find the closed loop eigenvalues, then I can simply find the eigenvalues of this system, this matrix, right? Hence, we can write, hence, by selecting K, we can place closed loop poles at desired locations. What I have discussed before, that how to shift the poles from some place to other place. So I have explained somewhere in the first page. So note that K is also a vector, and for a plant of order n, and if there are inputs, size of K will be is R plus n. This is simply you can find from the relation between the U and A matrix. Now, so this is how we'll be designing controller for this particular simple system. For this simple system, if the system is regulator, if the desired state should be zero, if it is zero, then we get the augmented system like this. Now we'll take an example and it will validate this concept. Okay, let's take an example. So we have system matrices given to us A equal to 1, 0, 0 minus 2, and B given to us 1 minus 1. Okay. Design full state feedback regulator. Once we are tracking a constant value or 0 of the desired state, then it sometimes it is called regulator. If you are tracking a time varying function, then it is called a tracking algorithm. Okay. So here regulator such that closed loop poles are is equal to minus 0.5 plus minus I. Okay. So if you notice, these poles are in the left-hand side of the S-plane, so maybe somewhere here. Okay. So this is the poles which are in the left-hand side of the system. So we need to find a controller which will help to shift the original system poles to follow this trajectory. Okay, this is our target. So we have to design a controller. So as a control engineer, we can choose these poles. It does not matter because for this particular example, I have chosen this, but you can choose any other values which are stable poles. So based on this, you can design the controller. So first we have to try the poles location. So of the original system. So let's find, so if it is already stable, so there is no requirement of designing controller. So that's why let's trace the pole location of this original system. Okay. So let's do it. First, check the pole location of the original system. Okay. So here you can use this characteristic equation Si minus A. This is how we find the eigenvalues. So eigenvalue is nothing but roots or poles. Okay, this is something. So here we can find a sign s minus 1, 0, 0 is plus 2 equal to 0. And from this we can find s minus 1 is plus 2 equal to 0. Wow. So here, if you notice carefully, there is one pole of the original system in the right hand side. You can write here the location of the pole. So one pole is maybe here, another pole is maybe here. This is AC equal to 1 and AC equal to minus 2. So system is unstable. If any of the pole lies in the right hand side, system will be unstable. This is the knowledge already we have in the classical contours. So S equal to 1 unstable pole. Right. So now we'll design the controller part so that the response of this current system should follow this desired dynamics. Okay. So our next part is we have to, so since the system is second-order system, 2 cross 2 matrix, you can find the gain matrix in this form. So contour matrix, you can choose K equal to K1 and K2. This is the contour matrix. And the ACL we can find A minus BK. And where we can put all the matrices here, it will be 1, 0, 0 minus 2, and minus 1 minus 1, and we can write K1, K2, right? And from this we can write U1, 0, 0 minus 2, minus K1, K2 minus K1 minus K2. So you can write. And finally, we have the augmented matrix 1 minus K1 minus K2 and K1 2 plus K2. Okay, this is the system. This is the closed loop system matrix. Okay. And again, we can find the characteristic equation of augmented matrix or augmented system. We can write. So what do you have? We can write SI minus ACL equal to 0. So we have to find the characteristic equation here also. So this will, from this we can write. So what you have to do is equal to 0. From this we can write is 0, 0 is minus, we can write the matrix what you have found 1 minus K1, K2, K1 minus 2 K2 equal to 0. And finally we are having S1 to, I'm writing the final expression. Please check. So we are getting minus half K1 minus K2 plus 1 plus minus half K1 square plus K2 square minus 2 K1 K2 6 K1 minus 6 K2 plus 9 root. Okay. So these are the roots of this characteristic equation. Okay. So now you can use simply the minus b plus minus b square minus 4ac divided by 2a. Simply you can use this formula because it is second order system, you can even find. But now this is the basically roots of the augmented system, right? Now also you have to find the characteristic equation. Okay, one thing I also should write here the characteristic equation here. S squared plus K1 minus K2 plus 1 into S and plus 2K1 plus K2 minus 2 equal to 0. So this is the characteristic equation we are getting from the matrix. Okay. So now, and from this characteristic equation, we are getting these are the poles. Now that from the desired dynamics, from the desired poles, we can find the characteristic equation as desired pole we have given already. This is our desired poles given to us. So we can find the characteristic equation. So we can write S minus 0.5 plus I and into S minus we are having 0.5 minus I. Okay, these are the desired poles and from which you can write the characteristic equation. And if you simplify, we are getting S squared plus S plus 1.25 equal to 0. So now this is very interesting. So we are having one desired characteristic equation. This is our desired characteristic equation, and this is the augmented characteristic equation, right? This is the augmented system characteristic equation. So we can compare both the equations. We can compare the power, the SS coefficient and comparing. Let me define this the equation number, for example. This is 1 and this is 2, for example. Comparing equations 1 and 2, we are having K1 equal to K2 and 2K1 plus K2 minus 2 equal to 1.25, and from which you can write K1 equal to 13 by 12 equal to K2. So here our control gain matrix, the controller gain matrix, we can write K equal to 13 by 12, 13 by 12. So this is the control matrix which will come to the, in the controller part to design control input to the plant. So we can write E equal to minus, we have Kx. So we can write minus 13 by 12, 13 by 12 into x1, x2. Or we can write 13 by 12 x1, this is small x, minus 13 by 12. So now if you can simulate this program in MATLAB, you will get nice results. So this is the homework for you, how to write the simulating code for this case. So let's stop it here. We'll continue from the next lecture, how we can take the noise in the system and how we can design controller. So we'll have some example on aircraft system. Thank you.